Welcome to Pratidhvani, where we try to humanize science. I'm your host, GV Pawan Kumar. It is my delight, pleasure, and an honor to welcome a guest on this particular episode, Professor Deepak Dhar. Deepak is a very distinguished theoretical physicist, and he's extremely well known for his work on statistical physics and statistical processes and stochastic processes, including various different questions in, for example, statistical mechanics, such as random lattices and introduction of spectral dimensions in study of fractals, and also very interesting questions related to self-organized criticality, many other things related to physics. Uh, Welcome to Pratidhvani, Deepak.
Thank you.
Yeah, I should also mention to the listeners that Deepak is a very decorated scientist. He was also awarded the Boltzmann Medal in 2022. He happens to be the first Indian to receive that, and subsequently he was also awarded the Padma Bhushana in 2023. It is an honor to welcome you, Deepak.
Thank you very much.
So, Deepak, as we do in Pratidhvani, the conversation will be biographical and also mixed with the scientific aspects of your life. So, tell us, how did you develop interest in science from your childhood? Give us a view of where you were born. What was the kind of things you did?
Okay, so my father was in the state judicial service. So I was born in Pratapgarh, and
Allahabad. Is it
it's next
next?
to Allahabad, in
Uh,
the eastern India,
yeah,
eastern Uttar Pradesh,
yeah, somewhere near Prayagraj.
somewhere near Prayagraj.
Yeah.
But I was there only for till I was 1 year old, and after that, my father was transferred to Agra.
Mm.
And there we stayed for 2 years. Then he was transferred to Muradabad, and there we stayed 3 years, and so on and so forth. So I've been into many different towns in Uttar Pradesh, and Pratapgarh I never went to afterwards. So far, we have passed through the city on car, on way from A to B, but we have never been inside there. I don't know anybody in Pratapgarh per se. So, okay, it is just an accident of birth. Uh, how did I develop an interest in science? I think it was my father who encouraged me to look beyond IAS services,
Yes,
which
yes.
was sort of the hang up of a lot of people in India at that time, and in Uttar Pradesh especially. This was not, of course, when I was very young, but even from my fifth grade on and so on, he would try to tell me that there are other things, and gave me all kinds of small books about science. I remember in particular there was a British magazine called Understanding Science,
Mhm.
which was sort of equivalent of Science Today, which was the Indian publication at that time, but Science Today started much later, and this was around 1960 when I was 10 years old. And he would buy these magazines from the bookstore. Uh, I think he was the only one in that city to get this copy, so it was special order roughly. And being a British magazine, it was kind of expensive for Indians. But he used to manage, and get me that book and ask me to read them. And they were written in English, and I didn't know enough English at that time. But I struggled and managed to get learned little bit and understand half of it, and kept the magazine and learn it later, and so on and so forth. So that is roughly how the interest in science started. I think I was good in mathematics or in academics in general. So mathematics has its own charm, and you can start appreciating the beauty of Pythagoras theorem or something, which is true for most people. There are many students who can do this. So that was one fascination, and I think the distinction between science and physics and mathematics was realized much later.
Mm, mm.
So at that time, it was all these things put together, and So we just used to learn whatever was taught in school, roughly speaking, plus a few books on the outside. At that time, when I was 10, 12 years old, I couldn't read so much English,
Mm.
but I could read all these Hindi novels in translation, Hindi novels of Bengali novels in translation,
Wow.
and stuff like that. So we learned a lot of them. In summer, we would go to my maternal grandfather's Nanaji's house, and he had a lot of old Chanda Mama
Chandamama. Yes.
stored there. So we could read all of them in the summertime. No, there's nothing else to do. You cannot go out. So we used to read a lot of them, and so I got to learn about a lot of stories from Puran and Arabian Nights and all kinds of stuff, which used to be well presented in Chandamama at that time.
See, this anchoring of knowledge in stories
Hmm.
is something which, as scientists, we also do in a slightly different context.
Hmm.
When you are getting exposed to these kind of stories during your childhood, has it been kind of implicit or explicit into your mind that this is a way of thinking by any chance during that time?
No, I thought it was just an interesting thing.
Hmm.
So, for example,
Hmm.
you listen to music. I think it's very hard for young children to describe what they are appreciating when they are appreciating music. Of course, it has a nice beat and it has a nice storyline or some such thing. But beyond that, one doesn't really think much. But you can say, oh, I like to read stories. So that was the status at that time. And one could see these are imaginative stories
Stories.
and they have some sense of humor also at times. Not Indian stories so much, but British stories quite often have some sense of humor
Humor.
in
Yeah.
them, and that was also very nice. And I think this came much later. But for example, this Alice in
Yeah,
Wonderland
listen.
is really a remarkable, and I can read it even now and enjoy it a lot and things like that.
It's also deeply mathematical.
Of course,
Yeah.
not very deep mathematics, but
Yeah.
very interesting that it
Interesting.
is presentable to 8-year-old children or some such thing, and at least some of the stuff they can appreciate very well,
Well,
even at that age.
true, true. So, which means that you are also kind of getting introduced to the world of literature.
Yeah.
And as you mentioned, translation is one of the
Hmm.
important things. Growing up in 1960s, the trend of translations probably was still prevalent and is still going on. Uh, but my only concern is that why did that not happen in sciences?
No, so we actually, this is a little bit later, but
Mm.
around when I was in 10th grade or
Mm.
so. But we used to get lots of books in English from Russian publishers, Mir
Mir,
publishers,
yeah.
because those were the cheap books available in Numayesh, or things like that, while the American books would be very, very expensive.
Expensive.
These were very cheap. And they were actually translated, very nice physics books,
Yes.
chemistry books,
Yes.
story of elements, things like that.
Yes.
So we learned a lot of science also through these kinds of books.
Nice, nice, very, very interesting. So, how was the schooling experience, Deepak? Like, you felt welcome? Did you enjoy?
Okay, I mean, at that time it was not an idea of enjoying school, it was just go there. But one thing which I still remember, which was true at that time, perhaps still true, we used to move from city to city. So
Mm.
I would often come to a class, when new class, where I'm the only newcomer and everybody else knows everybody else. So then there is sort of all the previous students kind of try to bully you in some way. So that is there and unavoidable. But I was very scared
Mm.
to go to a new school for a few days, 4 or 5 days. After that, things renormalized, but the first few days were always fairly stressful. You don't know anybody. Then you
Mm.
try to talk somebody. Sometimes they snub you down and things like that. But that's part of life.
Yeah, especially for boys.
Hmm.
I of course studied in the same school up to 8th standard. I
Hmm.
also had a transition
Hmm.
after 8th standard. But I have seen that people, especially boy students,
Hmm.
who make a transition, sometimes I have to really worry about this.
Hmm.
This bullying aspect,
Hmm.
especially, is a major concern. And
So I was somewhat protected.
mm, mm,
Because my father was some government officer, so he was
mm.
not so lowbrow. And then I used to get good grades.
Ah,
So soon enough, people would stop doing
doing
that kind of bullying. But at least in the first few days, it used to happen.
nice, nice. Did you also pick up your interest in physical activity then? Because I will come to that
Huh.
point later on. But I know that you are also very physically, active.
No,
And
so actually, I was kind of very small in
mm,
size
mm,
and but not very good health, scrawny
yeah,
and introvert. But actually, it was around 12th grade. My father insisted that I should get some more physical activity. So he would take me out on morning walks and make me jog and things like that. So he was actually he studied in Allahabad University, and in Allahabad, he was the cross country race champion.
wow. Okay.
Okay, it's a university championship, but
Yeah.
still,
Even then, it is a
but at least he encouraged me to do this. He encouraged me to take swimming lessons and things like that, which didn't work out very well. But at least he was from his side, he was insisting that you should have physical activity. After some time, I started enjoying walking a lot,
mm.
and I still jog a little bit
Yes,
now and
yes.
then.
Yeah. Yeah, to the listeners, I should mention that Deepak is a very regular in the mornings because that is
Yeah,
one place we also meet quite
right.
often, and he's been kind of inspirational to a lot of us to be regular.
So what I
Yeah.
realized was that unless you have good physical health, you cannot do anything. So my capacity to work becomes zero whenever I'm not well.
Absolutely.
And so for me, it is almost necessary to go to morning walk. Otherwise, I find that in 2 or 3 days, I become somewhat unwell physically as well as psychologically.
Yes, yes.
So, so I do it as a maintenance activity.
Activity.
But you may enjoy it, you may not enjoy it, but you just have to do it.
Absolutely correct.
So at
Absolutely.
one time, some friends they were saying, "Oh, you jog so well." So one day I decided, okay, I'll time myself. So I
Okay.
timed for 400 meters.
Mm.
My speed was one third of the Olympic speed.
Well, by that would also be scaling to a lot of other things, right?
Yeah, no, so, but I mean, so the point is, I was never going to become
Yeah, yeah.
a sports star,
Sports star.
but it was just to do, just to keep happy and maintain your
Yeah.
health a
Yeah.
little bit.
Now, this is a very important point what you're mentioning. Of course, we'll elaborate a
Mm.
little bit more once we also discuss more about science. Because the fact that the physical health has a reinforcement on the mental health,
Yeah,
and that reinforces the way you work is
yeah.
very, very important. And this is an important lesson a lot of us can also take away from that. So, proceeding further, now that you're kind of getting good education,
Mm.
and in 1960s in Allahabad, the university I was very well known,
Mm.
including people greats like Meghnad Saha and others were also.
Saha was by that time actually dead in
Oh, okay, yeah, that
1960.
it's already done, but there
Yeah,
was a legacy of that
there
particular.
was in Uttar Pradesh. It was sort of still considered the best university.
Yes,
I think
yes,
that would be fair to say.
fair to say.
And but still, there were very famous literary figures
Mm.
there: Jaishankar Prasad, Mahadevi Verma, um, Firaq Gorakhpuri,
Wow. Okay.
who used to be in the English department. It's
Department.
sort of very funny, but that's the way.
Isn't it? That's
Yeah,
even, for example, you are Anantmurthy, who wrote all the time in Kannada, Jnanapita Award winner, was actually in Mysore University English department.
huh.
Yeah, it was a similar kind of
Yeah.
thing.
I
So
think
that,
this was colonial legacy,
yeah.
but the English department used to provide some new ideas, and
Mm.
you could get what is meant by criticism. while the corresponding stuff in the other departments in languages was not really available. There will be one or two good critics, but not too many, and you cannot, at least that there are not enough teachers to be able to provide a good level of instruction in those subjects. So that is why those departments were not considered very highly.
So in that sense, you had a smooth transition from school to kind of college. You probably proceeded at the same place, right?
No, so okay, my high school was in Meerut Government
Oh.
Inter College, and 12th grade, 11th, 12th I studied in Muzaffarnagar, and for bachelor's I went to Allahabad University, and masters in Kanpur, and PhD at Caltech.
Yeah, we'll come to that. We'll come to that one by one.
Yeah.
First, give us a little bit of flavor of your MSc days, the bachelor's days, before we go into the masters, especially in the University of Allahabad Physics department. As we mentioned, there were very big names. It had a very good legacy of that particular physics department, especially.
So I was actually sort of very introvert person. And the university did not encourage too much interaction between students and faculty.
Strange.
And we were shy people, and the professors were big shots, and we actually never met many of them outside the lecture room.
Wow. Okay.
So no, I met 2 or 3 professors but that was sort of outside the lecture room. Otherwise, our interactions were restricted to he gives a lecture, I take notes, and like that. So I was not very happy as a student in Allahabad.
Okay.
Because it was not very stimulating environment. But anyway, so I had managed to get something called Science Talent Scholarship.
Yes.
So
right.
that helped a little bit, because for it helped us meet other students from Allahabad or from actually all over India. So we got in contacts with them, and we could see, that is what subject is like, not just the textbook. And there was also a provision of providing a local mentor. In each university, the student has a local mentor. So my mentor was Bipin Kumar Agarwal, who was a very good physicist and also a painter. And so he had some interest beyond just physics. I don't think I learned much physics from him.
Okay.
But for example, you give me textbooks on physical chemistry, for example, which was beyond the textbook for me. And so he provided some general guidance, which was very valuable, in addition to whatever minor questions I would have about the subject itself.
Nice. So during this bachelor's phase, are you already developing some interest towards physics? Of course, this probably would be an honors program then.
No, there was no honors in Allahabad.
So it was just like physics, chemistry.
There was physics, chemistry, mathematics for a combination for me, and for other people some other combination.
So there was no biology then?
For me, there was no biology.
No biology. Okay. So what was the kind of stuff you were studying then? The kind of conventional topics?
It was very conventional. I mean, but I still remember that I read this book, Saha and Srivastav, Heat and Thermodynamics,
yes.
which is actually still very good.
Very good
and
book.
it sort of gives you some appreciation of the subject.
Yeah.
And I could, by that time, get all these other books on relativity and so on from summer schools, etc. So could learn those as well, which were not part of the textbook. So the fact that I liked physics was quite clear by that time. I enjoyed chemistry labs very much.
Interesting.
Because it was very amazing to see, you take this test tube with red stuff, red solution and green solution and join them and they become blue or some such thing.
Beautiful.
And these indicators where you drop one drop extra and it becomes pink. Before that it was fully white and the drop was also white. These kinds of stuff was very fascinating and amazing. And Yeah, so that was the bachelor's. I think the interesting point in Allahabad about bachelor's was that the best students were expected to appear for IAS exam.
Mm.
And the university would pride itself saying that this year 10 students cleared it or some such thing.
Okay, okay.
Okay, so
So it's been there for a long time.
it was their forte, that
Forte.
was the like nowadays it is Delhi. All if you want to be in IAS, you have to be in Delhi and
Yeah.
be coached there. I think at that time, if you are from Uttar Pradesh or Bihar, you would go to Allahabad, then be coached there to go
It's
to
like going to
IAS.
Kota nowadays.
Yeah. It was sort of like that. So, but then if you say that you don't want to appear for IAS, then you are looked upon with a very surprised eye. Okay, what's wrong with this guy?
Like people not going to engineering.
Right.
Fascinating, fascinating. So, which also means that you still have harbored very strong kind of preference towards physics.
Yeah.
Because which further takes you to IIT Kanpur,
Yeah.
your next
Hmm.
stop. So, was it a deliberate choice because it is already in Uttar Pradesh, or was it anything
So
beyond that?
actually, after 11th grade, we went to our first summer school, which was in Kanpur.
Ah,
And I liked it very
very.
much. For me, young guy coming from Muzaffarnagar,
Yeah.
all of us.
1970s, right? It
Yeah,
is
in
1970.
70s,
Yeah.
there were these things called punched cards, which many of you have not seen at all. But at least for us, they were just lying there on the side where very high advanced technology
Hmm.
was just around you everywhere and things like that. So
Nice.
that was very impressive. All the people who gave lectures in the school were very impressive.
Hmm.
And so that made me feel that one would rather study here than in Allahabad. And the same feeling was shared by other students from science talent batch, and all of us appeared, and all of us was taken in IIT, so
Kanpur.
like that.
Right. See, one of the important aspect of IIT Kanpur is especially during that particular time, and still the quality of the work and the science, the engineering which is done is very very good. The Kanpur of 1970s was actually considered as one of the top-notch cities in India, and it was the place to go and really study and also become a, let's say, a faculty member or something like that. Could you paint us a picture of how it was for you to enter that great institution?
Okay, so I was not awfully overawed by the Kanpur because A, I had seen, B, I had seen also my other friends who were applying there, and there was there was no written exam, there was an interview. I don't remember all the questions which were asked there, but I think I didn't do everything well.
Okay, good.
One question which I still remember was that, oh, you have this terylene shirt, and when you take it out, sometimes there are sparks. So where do they come from?
Nice.
So I was fully tongue-tied. I roughly knew there is some electrostatics involved, but the idea that there is spark and there is such a high voltage, etc., was not known to me. But then they asked some other questions about, can you expand cosine 2x in cosine x and sine x, and those kinds of questions I could do.
Good. Yes.
So I think I was finally selected. I don't think I had a very impressive academic career at Kanpur. I was okay. I mean, I got some 9.6 kind of average.
No,
No,
that's actually outstanding.
It is pretty
right?
good,
Yeah.
but not 10.0 kind of stuff. Like a person who does everything well.
Yeah.
But I learned in time that in order to clear an exam, you need to know very little, and you can get 10 out of 10 and not know much about the subject, which happened to me for quantum mechanics, for example. I didn't understand, but I still got 10 out of 10.
Yes.
Like that.
There lies an important lesson, because the fact that sometimes students do get out of out marks should not create an impression that their knowledge is also complete. And this is also true for a lot of people
Yeah.
in that sense.
So this is slightly out of chronological order, but let me just mention
please.
that I was an assistant of Feynman at one time.
Yes, we
And
got
one
it.
thing which I learned
Yeah.
there, which he taught me, was he asked me to grade the exam, which I graded, actually I graded the same way as the previous grader had done, which is that each week they would give 2 or 3 questions, and you submit the answers. By the end of the semester there are 20, 30 questions, and so the previous grader used to give 1, half or 0 to each problem. And I did the same. So he said, no, this won't do. You got to grade out of 10 for each question.
Okay.
And the point was that if you want to distinguish between 10 and 9.5, that cannot be done on the scale of 0, half, 1. And a good student needs to know that he's not perfect. He can do better. And that feeling is somehow lost if you get 15 people who get the first rank in a university exam. No, that is just of course, if you use grading only to throw out people, then it doesn't make a difference. Or to make people happy, so then give everybody the first rank. But it does give the idea that, this is the best you can do. But it is not true. You can do much better than whatever you did.
Absolutely correct. Absolutely.
And that feeling should be kept. And I think the grade inflation is a very bad thing which has happened.
I agree with you.
It doesn't happen only here, it happens also in US and so on, but it should be avoided as much as possible.
True. So in that sense, if you also look at the time which you are spending at IIT Kanpur, and Kanpur also has very good departments in basic sciences, and you are now entering after having good foundational kind of education at University of Allahabad. So now you're also getting exposed to physics because you are now specializing in physics. Uh, in what sense you are also developing your interest in slightly more advanced topics in physics? Did you also come across something specifically?
Following the textbooks, just learning them a little bit better. And no, I didn't learn much specialization at that time.
Okay. And you were then exposed to conventional classical mechanics, quantum mechanics, and other kind of things. And how was your experience there? Like as a student at IIT Kanpur, of course you are a distinguished alumnus of that particular place.
Yeah.
Now, and how was your overall experience?
So first thing which I can say is this: that okay, I finished my MSc at IIT and then I joined Caltech. In the first year, they still have courses there, which I took, but most of the courses were a repeat. And I didn't have to work very hard.
Nice.
So I think the courses taught at Kanpur at that time were comparable to or as good as the courses in the best places in US. And so that was certainly good. And so after that, I started trying to look for problems to work on research. So that took some time. And when I had gone to Caltech, I thought I will work in high energy physics.
Yeah, that was the place where.
But soon I realized that no, that is not my cup of tea.
Okay.
So I think it was like this, that the kind of questions they asked, the simplest of which was something like the scattering of pions with pions. So what happens if one pion hits another? And somehow I felt that I never have seen a pion in my life. So I don't know what's a pion. And so the whole question was very abstract. And of course, it was also phrased in this quantum field theory language. And the question of what happens when a pion scatters against a pion is embedded in some deep formalism of quantum field theory, which is very subtle. And you have to write all those propagators, do all those integrals. In the end, something comes out. That was my feeling. Of course, it was not fully right, but that is how it felt. And so I felt that I couldn't do this kind of high energy physics in which there was a lot of abstract G mu nu and various side nu, gamma mu nu, all kinds of symbols are thrown in and some integrals are done and something happens. So, and I must say that in the first year, we were taught something called advanced quantum mechanics by Feynman himself.
Wow. Okay.
And he explained these diagrams and quantum field theory and explained in some sense why they are approximate and not fully there, because all these renormalization problems are there and you have to understand them. And so I decided I want to do something other than quantum field theory. And it seemed like a reasonable thing to do was statistical physics because it has some nice structure. And then I learned of some problems of, cluster growth in solutions. It's called Johnson-Mill model, but doesn't matter the name. But you have a solution in which some crystallites grow and they keep on growing at constant rate until they collide, then they just join up. And in the end, everything is filled with these crystals. And what is the distribution of sizes of crystals and questions like this. So I explained to my person who was supervising me at that time that this is a question which fascinates me because it's a interplay between physics and geometry. He was trying to tell me to do something about solar wind.
Oh, interesting.
He was a astrophysicist. And I was saying, no, I like to work on this problem. So he listened to me politely, but told me, no, I think you should find some other advisor.
Oh, okay.
So eventually I found Professor John Matthews, who was very generous. His principle was that you should choose your own problem. I will explain to you, or I will supervise you, but I'm not going to do that problem. And he was very generous about what subjects the student can follow. So I started working with him. Then I would go to him and say, right now I'm studying this and doing this, and he would listen carefully, make a few suggestions, and it went on like this for a while. So eventually, at some stage, one learned about the Castelline's dimer model and so on. And I explained to him that this is the way it works or something, and I can do this much. And then he said, "Oh, next week," he told me that in the plane flight from someplace to someplace back to Pasadena, I was looking at it in the plane, and you can do it like this.
Oh.
So of course, it's an old solution to Castelline. But the point is that he didn't have access to Castelline at that time, and he was sitting in a plane, and he was able to solve it by himself there, and explain to me later how it could be done. That was very encouraging because otherwise, sometimes some of these fields look like they are great magic, and you have to be a magician in order to do this. But then I realized that ordinary mortals can also work in these kinds of fields. And then we just try various things, and some of them work, some of them don't work.
Wonderful. So we did not actually go to the specific transition per se from Kanpur to Caltech in your kind of chronology. So was it a deliberate decision that you choose Caltech, or you were thinking about other places?
Actually, no. I applied to 6 or 7 places in US, and luckily I got admission to all of them.
Wow, very
the
nice.
reason was simple. I got good score in GRE.
Okay.
So then it was a difficult choice which one to take. And I think I was just final criterion was the famous name. And so I went to Caltech. There were some other criteria. Caltech was paying a stipend of $200 per month. Some other place was paying $500. But I chose Caltech because it seemed much better, so like that.
Wonderful. Now, going into Caltech, the department itself is very reputed, and you were also teaching assistant to Richard Feynman. Listeners who may not be aware, you should be aware, Richard Feynman is one of the greatest physicists, and Deepak actually also took advanced quantum mechanics course from Feynman. So give us a little bit of gist about
so of course,
interacting with him.
Feynman was legendary person. We had heard of him in 10th, 12th grade.
He already had a Nobel Prize too, right?
Yeah, of course, he had a Nobel Prize. He also had these book lectures in physics, which students used to read. Even
is it? There was already.
It was already written around 60.
Yeah, you're right. Yeah.
And it was already well-known textbook.
Yeah.
Sort of people used to study it. So it was like God. And when he was giving all these lectures to the students, a lot of faculty people, senior people, 40, 60-year-old from other university will come and just sit in the back to watch him give lecture for 1 or 2 lectures. When if you are here, why don't you listen to lecture by Professor Feynman? So even famous professors will come and sit in for his lectures just to see. In seminars, he would be fairly stiff and ask all kinds of tough questions. And if you don't satisfy him, he is not easily, he will not keep on bugging you, but he will say clearly that no, that is not satisfactory enough kind of answer.
Okay.
And
you had a very close interaction with him, right? In the sense, you used to talk to him on the course, what you're teaching, and was he teaching?
Somewhat, not very
close.
I was very shy person, and he was a big chan. But we used to interact once in a while. So I was his TA for the second year of that quantum mechanics class. First year I had taken myself, 2 semesters. In second year, in 1 semester, I was his TA. But when I was at TA, I realized, I was talking to other students, and they would say that, Feynman is great. If you listen to him give the lecture, you think you understand everything. And after half an hour, you realize, no, you don't understand anything. True. And the reason was very simple. That for many students, they listen to the lecture, it sounds great and simple, but they didn't follow it up by repeating that lecture if you don't go back and read it again, then it gets lost. And so what you have to do is you have to actually go back and revise,
reconstruct.
Then it becomes part of you. And if you don't do it, if you try to do it after a week, it won't work quite as well. So that was one of the things. So, for example, people realized, even at Caltech, that lectures in physics, his famous volumes, are not good for undergraduates. They are good for more senior people who are actually wiser. So once you have had an exposure to quantum mechanics, then you can appreciate well what he's teaching. Otherwise, somehow it doesn't produce enough of a good introduction.
This is a very, very important point, what you're mentioning. Even as students, when I was also studying, the appreciation came only when I went into masters.
Right.
That because generally that was taught at an undergrad level. But once you become a master's in physics, you'll appreciate far more than if you read it right at the level as an initial textbook. So it also means that you have a kind of ringside view of this person who is very, very reputed. Did it also influence the way you think?
I would hope so. I think he was certainly very clear, and it was sort of one, I think, very important with him was don't get overawed by algebra.
Yes.
And he believed in some insight, and be able to see through the algebra.
Yes.
And so one of his standard sort of questions is that, can you derive this formula in the shower?
Nice. Typical Feynman.
Which is that, you don't have pencil and paper. Without pencil and paper, can you do this?
Wonderful. That's fascinating to know. This aspect, this is a so important aspect. You also use very, very rigorous mathematics in your own work. But having heard many of your lectures and also having interacted with you, what I've learned is that you can still present the work, uh, probably post facto later on, in such a way that people would be able to understand
Yeah.
what you're doing in slightly greater detail. In fact, this is a concern, especially students who are just starting in physics, uh, especially those who may not have had a reasonably good foundation in mathematics, or even some people who may have foundation in mathematics, but using it in physics is not the same as just doing only the mathematics.
Yeah.
So, what do you have to say for people, especially who would want to actually understand deeper physics using the machinery of mathematics? Per se?
So, firstly, I would say that this simplification necessarily occurs somewhat later. So, I'm working on some new problem. Then I try to find a solution, and I find a solution with great work, but very ugly, it involves all kinds of complicated equations and symbols. And then you have to ask that, is this the best I can do, or can I find a better solution which is easier than this? And okay, you work for 2 more weeks, and then you can simplify the solution a little bit, or more like that. So it's important to be able to simplify and not feel very proud of the fact that I can do this very complicated stuff.
Yes, yes, that's an important point. And the fact that you also have a physical picture in your mind probably will help you doing that.
Yeah, physical, I don't know. The picture in
Picture,
your mind.
picture, yeah.
Yeah,
I'm not call it physical because that might not be the same thing as reality.
Yeah.
But you may have a mental model,
Yeah.
which probably would be used to reconstruct
I
whatever.
think it is useful to tell here a one Feynman story
Yes.
for people.
Yeah.
So it's like this, that he was just talking to some reporter, and he was saying that, oh, it's very irritating. You are in the airport and people come to you and say, Professor Feynman, can you explain why you got the Nobel Prize? And at the airport, it's not the right place to explain.
Yeah. Yes.
So this guy just laughed. And he said that, well, you should just tell him that, if I can explain it to here, it is not worth the Nobel Prize.
Okay.
And they all both laughed, and the reporter went away. But Feynman kept worrying about this question.
Yes.
And after 2 or 3 days, he rang up the fellow again.
Nice.
And told him, no, I was wrong. If I cannot explain what I did to a high school student, and I don't understand it well myself.
Wonderful. Yes.
Okay.
Yes.
So, so that is the approach. And it says that complicated formulas which you cannot explain to your younger brother are not really full understanding. They can help you partly, but you have to decode a lot of those symbols. What is this psi actually, and what is this trace, and all those kinds of words which we use as code words.
Yes.
But they have to be deconstructed a little bit to get to the core of the matter.
Very, very, very profound, actually. This is also sometimes a concern for a lot of students who would want to get started with physics, be it experimental physics or theoretical physics, because you have to really decode. That decoding is a very important thing, right? Because the code is the same for everybody, but the decodes can be different.
Or it is not made by many.
Exactly.
So, I have been talking to students at IIT.
Yes.
So I realized, so I said, how do you go from A to B? Then they say, oh, we start with this, then we say this, then we say this, then we say this. As if the process of saying this is important for the understanding of proof. They cannot do this without going through all those steps and saying all those things. And all those things are like mantra, once you say this, then everything is okay.
Everything is okay. That's a very, very important point, because that leap sometimes also will give you slightly different
also one should not confuse invoking a lemma or something as a substitute for understanding. Okay, if you just repeat that, okay, then by somebody's lemma I get this result. It's not the same as you have understood what that lemma is. if you understood what that lemma is, then you could say the same thing without using that word.
Absolutely.
That is my feeling.
Yeah. In fact, this again resonates with what Feynman says that knowing the bird by
Yeah,
its name
precisely.
and knowing the bird
Yeah.
is two different things altogether. Beautiful. So I also am aware that you probably had also some interaction with Wilson.
Yeah. So if Wilson spent 1 year at Caltech.
Caltech, yes.
Luckily, at the time when I was a student there.
Yeah.
So when he came, I met him once, and then I think I met him 4 or 5 times total.
Oh, okay. So to listeners, I have to mention this is Kenneth Wilson, who is a reputed physicist, renormalization theory.
He was the founder of the new understanding of the renormalization theory. Renormalization theory was kind of invented by Gelman and Lowe in 1950, but I think it's fair to say that they didn't understand what they were doing.
Wow. Do you think so?
I would say so, certainly.
Okay.
If they understood it well, they would have explained it better. And they didn't understand it, and even people like Feynman didn't understand it at that time, because they only used to say you can cancel infinities and then you get a finite answer and stuff like this. It was only Wilson's understanding of what the renormalization actually means, which provided a fresh way to look at it and gave it much more power.
So he had already worked it out by then when he came to Caltech.
Yeah. He was actually my friend. H.R. Krishnamurti was his student and working with him at that time.
Wonderful. Yeah. So this means also that you already are getting the taste of renormalization, which is a topic which you also have used very, very creatively. We're going to come to that point later on. But were you also kind of getting exposed to those topics? Because the problem what you mentioned...
At that time in 1970 to 72 and so on, everybody in statistical physics was working on renormalization of phase transitions, critical exponents. That was the general direction of work. And it would be very difficult to work on something which was totally different. So I was exposed to this general idea. I was trying to calculate some critical behavior or the other myself. Fisher and Wilson had written long review articles which we used to read. Shanking Ma had written a book.
Still
all those things were already there, but they were new. But they were there. The book was there already.
Oh, Ma was already there.
Yeah. So all these things were there, and we were trying to understand them. I had done some calculation where I did some variational calculation. As a result of variational calculation, I claimed that the actual singularity in the Ising model is always a first order transition. Totally wrong.
Okay.
But I was a student.
You got some.
And I showed it to Wilson, and he nodded his head. He said, yes, it's a variational calculation. That's what it does.
Wonderful. So, was it a very nice experience for you to be in?
I think it was very nice to be able to see him. I don't think I directly learned too much from him in my next research paper.
No. Okay. Interesting. So tell me also one more story, Deepak, which you have told us regarding you having a party in Feynman's house.
Okay. So this was actually very early. I had just arrived at Caltech, only 2 weeks old or some such thing. And then some senior students whose names at that time I didn't know came and said, let's go to Feynman's house.
Okay.
So what was the occasion? So it turned out that Feynman had gone on a sabbatical to Japan. And, since it was several months' time, he wanted his house to be the housekeeper for the house.
Oh, yes.
And he got a PhD student in our department to be the housekeeper. And he had a German girlfriend who was also a physics research scholar. So they were taking care of the house. And they had instructions, don't go into that room and don't do all this. But other than that, you can use the house. So he just invited the students from our dormitory, because he was living in that dormitory, to go there. So we went there. We didn't do too much. We just stayed 1 hour or so. We drank some orange cider or apple cider and stuff like that, and just came back.
Okay.
But it was at Feynman's house when he was not there.
When he was not there. Interesting. Very, very, very interesting story. So now you already have got kind of an overview of the statistical physics.
Yeah.
Having now started working on a problem which is somehow also kind of getting connected to what you're going to do a little later. Tell us a little bit more about the
Okay.
research problem.
Yeah, so during this first year, I also took a course called States of Matter by Goodstein, David Goodstein. And he was an excellent lecturer, and one of the things they were working on at that time was helium adsorbed on graphite. And phase transitions in them, and I guess it was known that there is this Kosterlitz-Thouless theory, and which is somehow useful or some such thing. But they were trying to do it themselves and doing experiment and see how it works and so on and so forth. So Feynman also worked on this problem. He never published that stuff, but he did obtain some sort of mean field solution to this problem, which is singular mean field solution. I will not discuss that part in detail here. But those people, he discussed it in class, and we were thinking about it. So in any case, I was getting to know about renormalization group, and then there was a paper by Nelson and Fisher, which discussed renormalization on fractals.
Nice. Yes.
And before that, there was, of course, this famous paper of Wilson and Fisher on phase transitions in 3.99 dimensions.
Nice. Interesting title, right?
That's the title of that paper.
Yeah.
And of course, the question asked is, what is 3.99 dimensions? Which they didn't answer very well. And later, this other paper shows how to construct fractals, which are actual objects or explicitly constructed fractals. You can define Ising model of them, and then it has a critical exponent. You can ask what is it, how does it depend on the dimension of the fractal. So that idea interested me very much. So I tried to do this. So I took the fractal which they had studied and said, okay, let us study some other model on this fractal. And the simplest model one can think of is the spring mass model.
Okay.
So, but working that out was somewhat non-trivial, but in the end, you can actually get the exact spectrum, and it shows the low frequency density of states has a power of behavior which is different from the dimension which is obtained by the box counting method.
Nice.
It was a different dimension. And so that is what I found, and that was that was my first paper to discuss this stuff.
Wonderful.
Actually, it was not really the first paper, it was the second one. The first paper was a small half-page note about line stretching in turbulence.
Wow, okay, so that's interesting. So you have a connection to turbulence right at the beginning.
Yeah, no, so actually I attended, I was at Caltech and I didn't know what to do. So I was studying all kinds of lectures.
Yeah.
So there were some lectures by Safman, who is very well-known person in fluid dynamics.
Yes.
And he gave a proof of this line stretching in turbulence that on the average, the mean squared deviation between two marked particles will grow as a function of time. And I just, he gave the proof. He involved some complicated eigenvalues of matrices and something. So then I went to him, I told him that, look, but this proof can be obtained directly by symmetry. It was 4 lines, really. And he said, oh, okay, I will look at it, I'll get back to you. But after 2 or 3 days, he came back and he said that, yes, I agree with your result is correct. And it is much simpler than this much more complicated derivation given in the standard treatment. And so why don't you write it up? So I was somewhat reluctant to write, saying there is just half a page, 4 lines. Can you publish it? He said, no, it can be published. So I sent it, and it was accepted for publication. He was the editor, of course.
This was in which journal?
This was in Journal of Fluids, Physics of Fluids.
Physics of Fluids. Wow. Okay, this was not known, Deepak. This is very interesting.
So like that.
So because your thought process is also on that particular thing. Has this
No, at that time I was just looking for
looking
some
at
problem to work
work
on,
on?
and so I looked at all kinds of problems.
Because later on you also have come up with the spectral dimension
Yeah.
aspect of it. Was there any connection already, or
No,
not yet, right?
It was a connection in time, but
Not in not in the space. That particular very interesting, very interesting. So now you have worked on this particular problem, and you go on to work on the similar problems there in Caltech, or do you change some of the
No,
questions?
so after that I couldn't do
Hmm.
anything much in turbulence. So I decided to work on other stuff,
Yeah.
which is easier problems.
Mhm.
And so these fractals seemed
Hmm.
interesting. And there was another problem which I wanted to study from the beginning, is theory of melting.
Melting, yes. That
So
fascinates you even right now.
yeah, so we made up something or the other. It was a model somewhat interesting,
Hmm.
but it was not really a solution to the problem. But got me my PhD, like that.
Nice, nice. So, was there a specific model system were you looking at, or
Yeah.
what is
So
it?
there has been a theory
Hmm.
that melting in solids is a layer phenomena,
Hmm.
because while people know that you can superheat liquids,
Hmm.
you cannot superheat a solid.
Yes. Hmm.
And the idea was that what happens is when you heat it, the layer by layer they just dissolves away.
Dissolve. Yeah.
So, and also was also seen in simulation.
Hmm.
So we just took a model in which the lower layer is held rigidly fixed and in a periodic lattice, and the top layer is just harmonic springs,
Okay.
and they sit on an external periodic potential,
Potential.
which was taken to be sinusoidal. So it is sort of like a discretized sine Gordon model, it is called. Then by some transformations you can convert it into Coulomb gas, and it undergoes the KT transition. And that renormalization theory was known, but I sort of worked it out for myself in this system. And that was for my PhD.
For your PhD. So, which means that you are now having a good exposure of both in terms of the techniques and in terms of the questions, what you are now interested in. Are you also thinking about some problems which you're going to kind of work in, or you are just staying in the moment and doing what is necessary?
No, I was thinking of different questions. Many of them I was not able to. I didn't think of them that I have to write my next paper on this topic.
Yeah.
Just it looks like an interesting question. And in some you make some progress, in others you don't make any progress. But when I went to TIFR after PhD, then Professor Barma was there.
Yeah.
He was also same age as me roughly. And then he was working on relaxation in Ising models. And so I also started working on that problem. And then the next few papers we wrote on this Ising model, disordered Ising model and stuff like that.
We'll come to that particular point, because now tell us about the transition, because you headed back to India after you finished your PhD. Why, and could you tell us?
So I finished my PhD and I was looking for postdoc positions. I applied to 2 or 3 places in US and also to TIFR, and I think one more place in India. And only at TIFR I got an offer. I didn't get it from any other place. So I just came back. Anyway, I was not planning to settle down in US at that time.
Is it? Okay.
So I was planning to come back maybe after 2 more years or some such thing, but TIFR offer seemed like good, and so I just returned.
You just returned without any hesitation?
No hesitation.
That's quite fascinating. And this is roughly around 1970s, right?
78.
78. So once you are coming back, and you're also now bringing new kind of problems probably, and you're of course now getting into TFR and collaborating with Professor Berman and others. So this transition, was it also easy for you, or was it?
I didn't feel it as a transition. The main point about TFR was that the postdocs were not supposed to work with the professor. They just sit in the department and do their own work. So we reported to senior professors, but we were not working under them. We were not working on the problems they told us to work on.
Nice.
And so, so actually we just discussed with Barma, and he likes this and I like this, so we write a paper together in that mode.
that way. Okay.
So it was not a question of bringing problems with us or any such thing. It was just whatever problem seems interesting at the time, see if we can make some progress.
So what were the questions you were thinking that time, or what was the specific areas?
So I think one problem which I started working with Barma was relaxation in Ising models. And problems with disorder like percolation and stuff also started with Barma. And then we just went on from there.
Okay. So tell us about that particular phase where you also told us some time ago where you heard a particular talk and that triggered a specific question in your mind, and that led to all the very interesting questions which further.
Okay. So that particular talk is a little bit later chronologically, so let's not get there.
Okay.
But even before that, so in percolation like questions, so we just realized that if you put direction, then it becomes directed percolation, which of course was studied 10 years earlier, but not enough. And people 10 years earlier in 1970 didn't have very good computers. By 1980, they become somewhat more powerful. So we could do the kinds of stuff those people could do much better. And there were some interest in other places also in this new problem, directed percolation. So we just didn't do very much. We just did a Monte Carlo simulation.
Okay, nice.
Which is a starting thing for anything. And it was Monte Carlo simulation of a sort of new angle on the old problem, or new problem you can say, which later on became much more interesting. A lot of people picked up. So it was impactful paper for me because my first and second paper were not appreciated very much in the beginning.
Okay.
I think this fractal dimension paper started becoming well known only after it was rediscovered by Ramal and Toulouse 5 years later.
Oh, wow. Okay.
But they were kind enough to refer to our earlier work. So, so it was like that.
Wonderful. So, which means that you are already kind of looking at percolation and related questions. This is also the time when you are transitioning from a postdoc to a faculty member? Or,
No. So the transition to faculty member actually occurred in 1980. I joined in 78. 1980, I was made a regular faculty member, and all these papers on directed percolation came around 1982.
1982, yeah. So during that time, are you already thinking about that specific model systems, what you are working on, or are you also thinking about the abelian sandpile?
No, sandpiles came much later.
1980.
So I don't have great research plan for the future.
Okay.
I only look at lots of interesting problems at a given time and see if I can make any progress in any of them. If I can make some progress, then I decide that is this publishable or not.
Yes.
No, so, one should appreciate this point, because of course you can make some tiny progress on some problem. It's a little bit of a progress, but not good enough to be reported to, so then you make a threshold that if it is better than this, then I will publish it, and we go ahead with that, and not have any grand plans for goal ahead. It's just sort of random walk in idea space.
Idea space, nice. That's a nice way. Random walk in idea space. So tell me about that idea space now. In roughly around 1980s, probably 1985 or something like that. You were also then, having your own group. And
there was
no group.
No.
Oh, okay.
So
Interesting.
it was very interesting. In TIFR at those times, there were very few students. There were roughly 3 or 4 students in the whole department in 1 year.
Wow, is it?
And most of them used to do high energy.
Okay.
So in condensed matter, there'll be 1 or 0 per year.
Oh, is it? Okay.
And those students typically would be registered with the senior professor. Professor Sudhanshu Jha.
Yeah.
And so we didn't get to have guide a student until pretty late. My first student was Satya Majumdar in 1990.
Wow, that's late. Yeah.
Yeah, so till that time we didn't have students to work with us.
See, Deepak, this is something which is very interesting.
Yeah.
I would like to get your thoughts on this. When you become independent faculty member, at least the convention nowadays is that you immediately start the group. Uh, and here is a case where you are almost kind of working on your own problems alone, almost.
No, so we
or
had
you're
a group, but we
interacting.
had a group with Professor Barma. I mean, these were two faculty members, if you like. But there was one postdoc at that time, Mohan Fani, and but he left after 2 years to make his own company or something. But
So,
that was the level of group. There were not too many students at that time.
Which also means that you are thinking mainly by yourself.
Yeah.
And you will have to do everything.
Yeah.
It is sometimes, this is again having experienced this academia for last 15 years now. I have also found that, of course, building a group is important. Things that element of being in your own problem space is sometimes very enjoyable because you can ask questions which only you are trying to address.
Yeah.
And if you make a progress and you think about it, you also feel that you are doing something. That's much easier to do in theoretical physics than experimental
That's
physics.
true.
But even then, as an experimentalist, I also feel sometimes, and that's the reason I also do some small things on my own. But tell us a little bit about that independence of thinking, because that is a lesson for all of us to learn a lot.
Yeah, no, so I would say that it was one of the things which TIFR gave us was freedom of work. In the sense, we were not asked too many questions about what you are doing. So long as at the end of 2 years or some such thing, you have some substantial work to show. And so I think I'm certainly grateful to them. There's just one tiny story I can tell about that phase.
Yes, please.
I was a young faculty member. Professor Rohini Godpole was a postdoc.
Oh, wow, is it? Okay.
So we were used to work together in the night on the computer there,
Nice.
So one day, one of her younger sisters came there. And so she was showing them the place around that, okay, this is where this is and this is. And, then she said, oh, this is all very great. So how much do you have to pay to work here? Which, of course, all of us laughed. But, that was the point. The point was that we felt that it was a privilege for us to be able to work there and do whatever we want. And I think by today's standards or whatever standard, the pay was not so great. But it didn't seem to matter much.
The life was also slightly simpler then.
Of necessity.
Of necessity, yeah. Because that is something kind of irreversible, unfortunately.
Right? Those things are sort of boundary conditions. You live in a society.
Yes,
you cannot, the pay scales at TIFR cannot be very different from the pay scales in some other place in India. So they were all comparable, and but the freedom to work was special and new, which was not there in other places.
Beautiful. So TIFR is also a place which has many other interesting research kind of areas, and your contemporaries also are very, very well known in various different fields. How was your interaction?
So we used to discuss stuff with people in computer science and people in nuclear physics, astrophysics, like that. And so we discussed, but I didn't get to a stage where it could be a publication. But certainly for richness of exchange and so on, it was there. And I guess it is possible that those people benefited a little bit by my comment here and there. But it was not reach a level where I would become a co-author.
So it also is a great place, physically a beautiful place. And it probably would have also positively influenced your lifestyle.
Yeah, no, so because we took it for granted at some level. And only lately I have appreciated how much of the things we get we take for granted.
Very nice.
So, I was recently, we went to the hospital for my wife's doctor. She's a very renowned cancer doctor or whatever. And we were telling her that, oh, yeah, but IISER campus is very nice. And she said, yeah, all these government jobs have good facilities. Or So, like if you talk of IISER to an outsider, you will complain about, so we have this funding or that funding or this or that. But the fact that you have such a huge campus is actually not available to very, very rich people in other areas.
Absolutely correct.
Okay,
Absolutely.
and that somehow we are used to. Even if I go to Lucknow University, it will still have a pretty good campus actually.
Yes.
And that the university is still able to provide, even if they don't give you a lot of intellectual stimulus or even academic freedom or all kinds of stuff. So, but those things we often take for granted. And at that time, certainly I took all of this for granted.
Yeah. True. That is something which is very important. What you mentioned is so correct, because there is also a very famous poetry in Canada where the life is all about going from have-nots, from have to have-nots. So the moment you get something, your focus becomes something which you don't have. So you will not appreciate what you already have in that sense.
No, so in a sense, I would say it's certainly good to not be satisfied fully. You should always try for something more. There's nothing wrong with that. It is actually very desirable. On the other hand, being always sort of complaining about things you don't have is also not the right attitude.
Exactly.
So something in between is necessary. And a good balance is what is needed.
So correct. So kind of important, especially for generations who are also building stuff in their own careers. Sometimes this is an issue, right? Because they might actually get bogged down. But there is also an intellectual life which probably can still go on. And,
no, in particular for students, PhD students in India, I feel that they are not striving hard enough. They should be much more ambitious, but they say, oh, we are doing okay. I've written 2 papers in the last year or whatever. But is that good enough? Shouldn't you try for more, better quality papers? Not necessarily just in numbers, but better quality. And I would say that the same person, if he worked a little bit harder, could do much better. And that is important to realize, that it is not just satisfaction or being satisfied with less in physical terms, but also intellectually. You should not be satisfied all the time.
True.
At my age, one should start.
No, you are probably the most productive person I have seen.
So one has to worry about this. That can one, okay, now I'm 70 plus, so I should be satisfied. I cannot hope to do much more. But no, you can try. It may not work out, but you can try. That's the way.
Wonderful. These are golden lessons, and listeners, anybody, irrespective of their age, this is something which we'll have to register in our minds. So,
actually, on this thing, I can tell a small story. It is not related to me really, but it's a friend story.
Yes, please.
So my friend Sriram Shastri, he went to Bell Labs, and he was telling me this story that he was a postdoc at Bell Labs, and one day P.W. Anderson came to his office.
Wow.
And told him, oh, these things are very bad. I haven't written a PRL in last 3 weeks.
Last 3 weeks?
Some such thing. I wasn't there, so I don't know the actual story, exact words, but something like this.
Anderson telling that.
Yeah, so at that time he told this story. I thought, how stupid is Anderson? How can he say something like this? Why should he bother with one more PRL? But the point was actually not, Anderson was not saying this for himself. he was saying this for Sri Ram.
Okay.
And he was saying, you should be writing one more PR
Yeah.
ad in the next 3 weeks or some such thing, right? That's what he was trying to convey.
Convey. Okay, that's
But
interesting.
the way he said it was that I haven't done any interesting work in the
Mm.
last few weeks, years.
Mm. Mm.
And that one should worry about.
Absolutely correct.
Even Anderson has to worry about.
Even the great Anderson had to. Right. So we'll proceed in the timeline. Now coming to some, super duper work. What is very strongly associated with you. So coming to roughly around 1990s.
Yeah.
Please tell us what is the kind of questions you're asking.
Okay, so actually it all started with a talk by Pierre Bach.
Yes.
He came to Bombay and he gave a talk about his theory of self-organized criticality and how it explains everything in the universe, from water flow in river Nile to solar flares and to earthquakes. And then he described this model of sandpiles, which is so-called the Bach-Tangvisenfeld model. And basically we were not very happy with this talk because very strong claims were made there. And so we decided, let us try to see what happens. Then we were working on this directed percolation and stuff like that. We said we should sand piles, there is a preferred direction, so things should only fall down and not up. And so we modified the Pierre-Bach model to say things only fall down, what will happen? And Ramaswamy was there also as a postdoc at that time. And so we decided, let us study this problem. And he set up a numerical simulation code, which is not very tough to write in 1 or 2 days. And we saw that it looks like the critical density is half.
Okay.
Which is sort of very suggestive.
Yeah.
Then we said, can we prove this result? And it turns out you can prove this result. And then we tried to find some other things like what is the size of distribution of exponents, and all those could be done. The point is that this variation of the sandpile model to preferred direction makes it much more easier and tractable. And you can solve the model exactly in all dimensions immediately without too much work, without heavy mathematics. And so that was very useful for us. But then we got interested in the problem. Then you can see some structure. Then you can try to extend it to non-directed problems or partially directed problems and so on. And so that is how that foray in the field of self-organized criticality started.
So were you aware that what you were doing actually can turn out to be something very important? Or means you had a hint because the motivation for the problem is already there, right?
Yeah. No, so we had some general idea that it's an interesting solution. And there are many other people who are writing papers on this subject. It was considered a hot subject at that time. Then there was some school in Kathmandu where Kedanov had come to give some lectures, and I also gave some lectures on this model. And he was appreciative, and he said, this is a nice work and something like that. And that was the end of that, sort of. But I mean, the fact that people appreciated the work soon after it appeared was very nice. And, that's the way it has been.
Fabulous. So now you take this particular problem and further proceed with it. And you also actually look at some specific issues related to how it evolves. And could you tell us a little bit about
so that? We were just sort of trying to see this particular problem and extend it if possible in other things. And of course there was some general interest which has been there for a long time in modeling of life or something.
Yes.
So we found that some patterns in sandpiles can be made some analogy with proportionate growth in biology.
Yes.
So we tried to develop that idea, and I think it is an interesting idea, which is somehow not sufficiently appreciated by biologists. But maybe after 5 years they will start appreciating it also.
Yeah, I'll come to that particular point because I want to also kind of pick your brain on way of looking at biology from physics kind of perspective. In this particular kind of chronological
Mm.
timelines, what we're talking about, it also is a time when you are really working with some very, very accomplished people who later on become very accomplished by themselves. Dhar-Ramaswamy and Satya Majumdar. They're all people who you actually also have interacted with. How was it that kind of
Oh, yeah, I think it was always very stimulating.
Yeah.
And these people are very smart,
Yeah. Yeah.
and it is pleasure to work with them.
Mm, mm.
And I'm
Wonderful.
sure whatever we managed to do would not have been possible but for
Yeah.
the common
Common interest.
interaction and common interest.
Yeah. And you also mentored so many people, including Abhishek there and other people who are by themselves now leaders in their own respective fields. So what has been your model for grooming young people?
Okay, I would say that the fact that these people were very good was not in doubt.
Okay.
And I think it was an advantage to be at TFR,
Yeah.
that we got very good graduate
That's
students
good.
at the entry level. So Abhishek Dhar would have been very good in any case, but then if you can work with them a little bit, then you can learn with them and they can learn from you at the same time.
Yeah.
So I think that was the mood.
Yeah.
We just get them interested in some problem and see how it works.
That's it.
Doesn't work equally well with each student. Some are better than others. That's the way it is. But so that is
Wonderful. Because I have also done an episode with Sujeshna Sinha. She also mentions the influence what you had on many of them, and it's a very strong kind of view which all I get from a lot of people, including having interacted with you, even among students who have interacted at ISER, is that you show, you don't tell. Meaning you actually show that you can do good things by doing yourself, and people have to just watch it and then learn from that. That's a very, very effective model of also showing people how to actually work effectively, which brings to a point uh, where person who is deeply motivated in science, like you are, um, is also constantly thinking about research. Uh, Tell us a little bit about your thought process of, let's say, picking a problem and thinking about that problem, and what is the kind of process you generally.
I would say that I try to think of several different things, typically 6 or 7 things at a time.
Wow, that's
And most of them don't work out.
Yeah.
So, but then you don't sort of feel unhappy about that, just you shelve them. And after 5 years, you can look at them again. And it may still not work, but it keeps your overall unsuccess rate lower. Because actually it is 10%, but then those 90% don't show up, then you can still say, okay, I got 2 interesting results in this year, like that.
Nice.
So if you don't try 5 different problems, it won't happen.
Very interesting.
Even with the best people.
Absolutely right. Very, very interesting, very important point. But how do you structure this in your day-to-day kind of work? Because if you are really thinking about so many problems, uh, time is limited per day. You also have other responsibilities, etc. So how do you go about now looking at
So
this?
nowadays, in my ripe old age,
No.
what I do is that if I get papers to referee, I actually try to understand them before I write a referee report, which is pretty useful, and it keeps me up to date with this, at that kind of subject, because this guy refers to 5 or 6 previous papers. I don't read all of them, but I read 2 of them. And that way I sort of keep roughly abreast with the subject without reading everything. That would be very hard. And so that is how I try to keep up with the subject. Of course, one has some hang-ups, and some new subjects I don't like, so I don't look at them at all. But try not to be too ossified.
The one characteristic feature, which I, at least having looked at little closely as a colleague in last few years, is that you also still work at an individual level, which is deeply motivating, especially for me personally. I felt one of the important lessons I have actually derived out of you is that you can still have work with students, but still you work on your own problem. which is very interesting. And tell us about that, having that problem which you're working on yourself, and how do you kind of prioritize and other things.
Okay, say I don't think there is any sharp division. Typically, you try to work with some student and you show him this is an interesting problem. Then they don't make any progress for 2 months. Then it is a little bit frustrating.
Okay, then you take it up and then.
No, so then you try to see yourself a little bit,
Yeah.
and then you explain to him, oh, this can be done like this. But it may work out, it may not work out.
Yeah.
And so, it is a give and take constant. And so I don't think I work fully by myself. But if I am not able to involve somebody else in it, then I try to do a little bit by myself still.
So this is a distinct advantage being a theoretician,
Of course,
because as an experimentalist, sometimes you don't have that privilege. Even if you want to do it,
Sure.
it would be difficult without, let's say, some kind of involvement of other people. But going to that particular division in physics, generally speaking, I'm slightly broadening the scope of the discussion, is that kind of division which is there historically in physics, about between experiments and theory. And there's also another fault line, I'll come to that later on, between applied and fundamental. To begin with this division, Deepak, I want to get your views, because you also have interacted with experimentalists. You also have actually contributed towards research problems which have direct implications in experiments. Tell us a little bit about your thoughts on this division.
Okay, I would say that the fact that experiments are tough and it spends a good deal of time. And also there are some, like if I actually did experiments myself, I would not be very successful. I will actually be a major failure. No, so because some people have different talents. I don't have a talent in doing real experiments. So I don't want to try to do that. I can try to persuade some experimentalists to do them, or I can work with them, or things like that. So that is what I do at times. Long ago, in 1980, we did an experiment with Professor B.M. Arora in TIFR. It was, making up some arrangement of diodes and doing some percolation experiment determining conductivity of the bulk.
Wonderful.
So it turned out that we did actually spend a fair amount of time and energy, not so much money. The total money cost at that time was 10,000 rupees, which still was low budget in those times. But then we realized that whatever we managed to do with the enormous amount of work and one scientific assistant, one could do in the computer in 15 days.
Yes.
So, for some things, it's not necessary to set up very complicated experiment to be able to verify some idea, which is what our motivation for the stuff was. So I would say that one should be careful in choosing the experiment. Absolutely. And the luxury of doing the experiment without having an idea what it will be, serendipity, is much harder in experiment than in theory.
Absolutely.
So you can have lower level of this stuff, that this combination somehow has higher TC than that combination of elements or some such thing. But that's the level at which you can work. You cannot sort of invent superconductivity from basic theory or some such thing, right? That is too far. And I think so this kind of division between theory and experiment is reasonable enough at a functional level. It's necessary.
Wow.
Nothing can be, it cannot be avoided.
Absolutely.
Okay. Like most of the theories you see today will not be able to do a good experiment. And okay, you can always find some people who write papers in theory and experiment together, but are they equally good in both? That will be very tough.
Very, very tough.
So it is just because now the subjects have diverged a lot and the things needed to to do a good experiment are slightly different from things needed to a good theory. It's just inevitable at some level.
True. That's true. It's actually. And the other division which I wanted to just get your input on is this applied and fundamental. And would you want to just?
So I would certainly. It's a very important burning issue of our time. We are theoretical people, and now the attitude of the society in general seems to be that fundamental research is not needed and you only need to do some applications. So, some work on various applications of some idea or the other are all they look for. Can this produce patentable stuff in 3 years' time? If you cannot do this, then it is not worthwhile. I would say that that very mercenary attitude to research is not desirable. You can put a total amount of money you give to pure theory versus experiment, 10% versus 90% or whatever is your favorite number, but don't make it zero.
Absolutely.
That is going to be counterproductive to this purpose you are trying to serve.
Absolutely.
Okay, so that is unfortunately it is not generally accepted because nowadays what happens is that people like, without, there are no names here, but people like mega projects as opposed to 30 small projects of 1 lakh each. I would prefer one project of 1 crore each because that shows more visibility. Perhaps it has even bigger impact on the whole. But at some other level, those small projects in small universities would have been good for the overall intellectual climate of the country. The individual research may not be so profound, but at least that keeps that person going.
Absolutely.
And unfortunately, if you stop that funding, you lose a research which will be hard to replenish after 10 more years because a whole generation of people would be gone.
Absolutely correct. You made a very strong case of small science. Small, I'm not talking about or anyway demeaning anything. Small in terms of even the investment, but it is something at an individual level. This is a music for my ears because that is something which I also strongly believe, because the kind of nature of work what we do, at least in our some of our colleagues, is to do with an individual level where you train a group of students. That impact, unfortunately, Deepak, sometimes doesn't get kind of more attention. The impact what you can have, let's say, on one student getting trained on one thing, they might get a job, they might also become good teachers. This is sometimes you cannot fit in the metrics, right? But this is actually a real impact which you are really having.
No, so unfortunately the metrics are very faulty, but they have been designed by wise professors like me. Not me,
I got
senior
it. This is kind of a overall thing.
And it's very funny actually that you can ask that how can these people would be so foolish that they will make up this metric, but they did.
Yes.
And the people think differently than me. That's all I can say. But if you look at the implementation of the education policy, I'm not discussing the basic, structure of the idea. The implementation has not been very good in the last 30, 50, 70 years, I think. That is why we are where we are, while smaller countries like South Korea can do much better than us in overall literacy levels and whatever.
Even recently, even Vietnam, for example, they have also been scaling up, even up to the level of manufacturing and things. There has been a lot of change. So, moving further, one of the questions I would want to ask you, slightly related to the things what we are now discussing, is kind of scientific way of looking at things in general. Not only within the framework of academia, but general public. You also interact with students. Recently, we had a very nice science day kind of festival where you also gave a talk on scientific temper and other things. Can you please tell us a little bit about how general public can and should start looking at things in slightly more broader scientific perspective?
No, so actually, I managed not to give the talk on scientific temper because I had a cold.
Oh, okay. Sorry, I missed that.
No. It was announced, but it was not given. But I prepared something for that purpose. And in that context, I realized that, somehow there is a perception that scientific temper is for scientists, but it's not true.
Yeah,
It is supposed to be true for everybody. And scientific temper just means that not having superstitious belief in various things without any cause. If I believe in something, I should actually have some reason for belief, not just somebody else said so. Of course, there is a different set of people who believe, really, faith, where they say that, it is given in this book or that book, and so that's all. I don't need to know anything more. And of course, at one time, that mode was quite useful. But I think in current world, it is not very helpful to think that way.
Fantastic.
It is helpful for a tiny majority of people who want to rule over others, for whom it will be easy to rule if they are ill-educated and bad. But for the good of the society, it doesn't work. There is things which we call superstition, which we don't want to believe in.
Absolutely.
Like if I eat some food while it is Chandragrahana, is it bad or good? Or if there is a story about Chandragrahan that Rahu ate up this guy, or Ketu ate up Chandrama, can I believe everything which is written in the Shastras? The answer is one should not believe everything which is given. There are lots of good things given.
Absolutely.
I should at least take them.
Absolutely.
But there are other things which I should explicitly say, no, this is a nice story, but it's only a story. And this distinction between what is a story and what is the truth should be kept in mind. There are speculative stories also. Like people say that at one time they didn't know what is the universe outside, so they guessed.
Yes.
This guessing is okay, it is allowed, it should be done. Even now people are doing this.
Exactly.
Right? But it should be sort of understood what that means and what that is, and even should be not confusing our idea of what it could be with what it is.
Very
right?
nice. Very nice.
And somehow that distinction is less present in current society than it was present in the intellectual world of 1947.
Yes.
So I'm actually mentioning Nehru's name
Yeah.
because he's the one who introduced the word scientific temper, and he thought that it's a good idea for the society to have this temper as opposed to blind faith. That's all. And I think the age when the society could work with pure religion based on faith would be difficult now. The religion we can have now is, of course, some religion is necessary, but it's very different from the religion which insists on various ceremonies. Like unless you wear this thread, your life is not good enough. And those kinds of things we don't want to believe in.
Absolutely.
And we should say explicitly, and we should not encourage people to do more of these superstitious traditional beliefs just because they have been done long ago. That's what I would say.
Wonderful. It is something very heartening actually to hear this, because as you exactly mentioned that it is to distill good ideas, to take what is really very kind of of forward looking and then take it forward, because nobody is asking to abandon the culture. It is to just forward the way of looking at the world. Very, very intuitive and very interesting. So the other question I wanted to ask Deepak was the talks what we have given about the very interesting relationship between physics and mathematics. In fact, I vividly remember, because I was in the audience, where you also gave very interesting thoughts on and also commentary on Eugene Wigner's viewpoint of how mathematics is very very useful in interpreting physical world, and you also had very interesting thoughts on that. Give us a gist about that.
Okay, so Wigner had written this article called "Unreasonable Effectiveness of Mathematics in Sciences."
Yes.
Okay, and he pointed out that it turns out that some ideas from mathematics are very useful in describing real world. And he gave an example which I will take 2 minutes to describe. He said, take a population, plot the number of people with a given height versus height, and it has some bell-shaped curve. and it can be described by the Gaussian, and there is some root pi which appears in the normalization. So where does the pi appear in the distribution of heights of people? So the point is that, of course, there is some complicated mathematics which goes in, and it's the integration constant, and it is the normalization or some such thing. But in the end, the idea of pi, which was the ratio of circumference to diameter, shows up in a totally unrelated problem, and that is what he called the unreasonable effectiveness of mathematics.
Yes.
Okay. And he gave some other examples which are all known to people, and so some of the things we can describe quite well using mathematics. But it still remains true that many other activities of equal interest to us in real world are not so well described by mathematics. So, for example, I gave the example of Tendulkar. He's playing cricket, and I doubt if having very detailed knowledge of the trajectory will be helpful, or can it will not help you hit better.
Exactly.
It is much more intuitive or whatever it is called, but it is non-mathematical. Whatever the skill you develop is non-mathematical, and there is not much hope that you will be able to do much better mathematical description of cricket in this way.
Very nice.
It will not help you play cricket better. So one should appreciate that mathematics is very nice and useful, but it has limitations. If I want to worry about how the society is going to be like 20 years from now, social engineering it is called, or whatever it is, again, mathematics has very little to say about all this. But it doesn't mean that question is not very interesting or important or shouldn't be tried or some such thing, right? So one should just not be very myopic and think mathematics is everything. And unfortunately, this point is not explicitly said very often. And the students, when they are impressionable, are given the idea that mathematics is God, and or next to God or some such thing. And I think that feeling should not be conveyed.
Absolutely.
Because obviously people have said it before that mathematics is the queen of sciences. Gauss said
Gauss,
but Gauss was a mathematician.
Exactly.
Like that. So so one should be just not be very sectarian in this and say that I'm sort of somewhat good in mathematics, so mathematics is everything in the world.
Very, very interesting and very important point, because these are all questions which are again revisiting us in the current times. Because if you look at also the fact that one of the elements which generally is sometimes lacking among students who are scientifically or trained in sciences or in engineering is the exposure to humanities. And one can see that there are negatives of not having got that exposure, where mathematics actually is not the central thing. Of course, it will have surely some role there, but it is no way as much as, let's say, physics or even chemistry or somewhere. And that viewpoint also was mentioned by E.O. Wilson long time ago. Of course, it was criticized by many people, where he was telling that, okay, in order to do some kind of biology, not all kind of biology, you don't really require full-fledged mathematical knowledge. And I am aware that a lot of physicists especially were little kind of upset by that particular argument. But there seems to be a real point there, and it closely relates to something what you're mentioning.
So I would say that our mind is a very complex and complicated thing, and it has many spheres of activities. So if you take a poem and try to understand what it means, and what is a good poem versus a trivial and bad poem, it is hard to tell. That notion of aesthetics is not a purely scientific notion. Even in science, we say this is a great theory, this is not so great theory. But there is an equation 2 plus 2 equal to 4. There is an equation e to the power I pi plus 1 equal to 0. Which one is a more profound equation? At some level, they sound equally trivial and equally good, right? Absolutely. But what you read into them depends on your background and how you interpret them, and not just the equation, but what it is trying to convey.
Very, very correct.
Right? And that depends on our prior exposure and training and that kind of stuff. And so I think it would be bad if scientists do not have any appreciation of music. Fortunately, scientists can quite often appreciate music. I cannot do it very well, but at least 50-70% of the scientists can appreciate music. I cannot say the same for people who are musicians, that 50% of them can appreciate science.
Precisely.
And I think this point should be equally harmful and it should be remedied.
Absolutely.
So, for common public, that is the scientific temper part, it is not important to know any particular scientific theory, but the overall structure of scientific thought should be understood, that there are things which are well established, there are things which are less well established, there are things which are well explained, things which are less well explained but can be understood, and there are things which cannot be understood even by God, So they said that behavior of hydrogen atoms I can understand. Okay. Behavior of single cells also are kind of understandable at some level. But the behavior of individual women species members, those are unpredictable even by God, something like that. So I think that point should be appreciated. And if there is a comment in the poetic world which doesn't make any sense, and sometimes you can just say it differently when it doesn't contradict or doesn't. So, there is a very famous saying by Walt Whitman. He said, I contradict myself, very well I contradict myself.
Very nice.
I don't know what that means. I don't know why he should be proud of this fact. So I'm not able to appreciate this point. Well, maybe that is just my limited understanding, but I'm saying that he wanted to say something, I'm sure, and he was not bothered about logical rigor. But couldn't he say it in a slightly different way, so that even I can understand what he's trying to say? Like that.
That's very, very, very interesting and very important. So this also brings us to another small connecting point, is your thoughts on biology, because you have worked in a field which has some kind of indirect connection to biology, and given the fact that the system is complex and statistical physics does play a very critical role in such kind of areas, how should one look at biology, Deepak, especially from a physicist viewpoint, because now it's one of the greatest challenges.
Okay, so I would say biology is a difficult subject, complex subject. So, and people have tried to understand it for a long time. And of course, there are some partially understood, some less well understood areas. So, what I would say is that the physicists sometimes provide a different way of looking at the problem, which is useful, even if it is not perfect, even if it doesn't explain everything. It poses a different set of questions, which is enriching. Maybe it doesn't lead to money tomorrow.
Yes.
Okay. So if I'm very, very money counting person, then I may not benefit. I will ask, what is the use of this? Even if you understand what is the point. But I would say it provides a different approach to a difficult problem, which has not been solved yet. And so to that degree, it is certainly very useful. And since I have a physics training, I will try to use my physics training to explain biology. Somebody else will do it differently.
Very, very nice, very interesting point, because the biology has become central in various different kind of questions, which is of interest to physicists nowadays. Also from conceptual viewpoint, also from let's say technical viewpoint and other things. Physics also has been extensively used, specifically statistical physics has been extensively used to even go and try to interpret larger kind of arenas of knowledge, economics and financial markets and other things. What is your thought on that? Is it kind of successful, and to what extent?
Okay, no, so these stock markets and stuff like that, of course it is partly successful. See, the point is stock market is there, and people are there trying to advise you to buy or sell stock A or stock B. And sometimes these theories are useful, sometimes they are not
They're
useful.
not useful.
By definition, they cannot be always useful
Yes.
because some people have to lose,
Have to use.
otherwise you cannot win. So it's a roughly zero-sum game, not fully, but anyway, roughly. And but the theories which are successful depend on being able to use the past patterns to predict short-term future or comparatively short-term future. Those things usually do not show up in published journals.
Yes.
They are very privately held
Yeah.
properties of the individuals who
What do
provide
you
you this, not free advice,
Yeah.
but paid advice, right?
Yes.
So I think they are certainly useful at that level, but at the theory of economics level, they are not providing anything extra just now. If I have an AI program which tells me which stock to buy tomorrow, okay, I mean, there is an AI program which helps me, some of the people. It will not increase the happiness of mankind by itself, right?
True.
So, okay, I mean, in those kinds of applications, there is not, physics is not playing a very important role.
Got it.
Statistical techniques are used
Useful,
sometimes,
yeah.
but those techniques are like, using a Gaussian distribution, and they can be used wherever you want.
So, last three questions I have. And the first question is, one of the points now just come to focus in Indian science is the question of inclusivity in terms of gender and also in terms of economic background.
Yeah.
These are very important points. And could you tell us a little bit about how, as a research community and as a scientific community, we should approach this problem? Any specific thoughts you have on this particular thing?
Firstly, I think it is important that some section of society not be disallowed some access to some kinds of knowledge. So like girls should not do science. That kind of attitude we should not propagate. And I'm saying this because in some countries right now, luckily outside Afghanistan, they don't want women to study at all or beyond fifth grade, right?
Absolutely.
We don't want to be in that society. We don't want to be like that. So, but do we want Shudra people to study science? Questions like this. So, I think they should be encouraged or allowed to study science. Now, historically, we have had reservations for 75 years, and somehow it hasn't worked in practice. So sometimes you need to put in extra, some slight advantage to offset the long history of disadvantage. Affirmative action कहते हैं अमेरिका में, यहाँ पर कुछ और नाम है, but we have the same idea and we have actually copied from the West. So I think those programs are certainly desirable at some level and they should be pursued sincerely.
That is the most
that is the hard part because in the past people said कि ठीक है reservation तो 70 साल से हैं. They were supposed to end in some years and nothing was needed. They will not be needed afterwards. It hasn't happened. So let it happen and then we can, the only thing people nowadays worry about is this too unfair, too much advantage given to the poorer sections and people much below required competence are being taken or some such thing. I would say that it is not written anywhere in the constitution that this should be done. And people should be allowed to say, selection committees, that no, we didn't find any suitable candidate. But if you cannot find a suitable candidate in 10 years, then there is some problem with your measure. Okay, so I am saying that selection committees don't be given a total free hand. It doesn't seem to work. But constraining them too much by saying that, okay, this year you have to take 5,000 people from this category. Okay, you take the top 5,000. It will still work out in the end, not too badly.
You're right.
But when the number becomes 2 and 3, then there is a bigger problem. Okay, then I think we should be more careful and not first set the gender and caste and various
Mm.
other 15 other parameters which are needed, and then look at which person satisfies all these conditions, and okay, maybe he's also a scientist. That should not be the approach.
Got it, got it. So my penultimate question is a request for you to speak in a few sentences in your mother tongue to our audience about what you are interested and what motivates you to do science.
ऐसा कुछ खास नहीं है, हम लोगों को बचपन से कुछ सीखते आए, तो उस विज्ञान में मेरी रुचि थी, उसमें छोटे छोटे गणित के सवाल होते हैं, उनका हल निकाल लेते हैं तो उससे खुशी होती है, आगे चल के थोड़े ज़्यादा मुश्किल सवाल निकाल लेते हैं, उनसे भी खुशी होती है, तो उसी तरह का काम करते रहते हैं।
Beautiful, beautiful.
तो हम लोगों के लिए जो है कुछ हद तक, पूरी तौर से नहीं, लेकिन कुछ हद तक साइंस की इंटरेस्ट इस तरह का होता है जैसा कोई पजल सॉल्विंग होती है।
सही है।
तो उसमें कहते थे कि ये तो यूनिवर्सिटी के प्रोफेसर हैं, अगर इनको एक ज्योमेट्री की प्रॉब्लम का प्रूफ निकालने को दिया जाए या एक रसगुल्ले का डब्बा दिया जाए तो वो ज्योमेट्री की प्रॉब्लम सेलेक्ट करेंगे।
बहुत अच्छा, बहुत अच्छा।
ओके, क्योंकि जो रसगुल्ला होता है ना, वो आपने एक बार खा लिया, उसके आधा घंटे बाद उसका टेस्ट नहीं बचता, लेकिन ज्योमेट्री की प्रॉब्लम अगर आपने नई प्रॉब्लम का हल निकाला है तो उसका टेस्ट काफी साल तक रहता है।
बहुत ही अच्छा, very very nice. So the final question, Deepak, I generally ask for the guest is tell us a little bit about your kind of influences in terms of things outside sciences, art, music, reading, and other things.
No, so my these hobbies or whatever has evolved in time. So when I was very young, I used to do a lot of reading. So in Chanda Mama starting, and then okay, Bengali novels or Rabindranath Tagore, Sharat Chandra, people like that, but in Hindi, translated in Hindi. Then in English novels also, and folk tales in general.
Nice.
Some music also I used to listen, but in time, my reading outside has become narrower. Because nowadays I don't read so many story books. But I read more biographies.
Biography, okay, that is one of my favorite
no, because I find that I'm able to get more benefit, whatever, psychologically, intellectual benefit from reading real life stories as opposed to totally fables, that kind of stuff. And so with time things evolve, but right now I'm not doing too much of literature study.
Nice.
And I did a little bit, but I.
What's your general relaxation process? Apart from running, which you do.
So I jog, which is helpful. It's just de-stressing activity.
Absolutely.
And some television I watch. Preferably not the news.
Nobody nowadays prefers that,
News में क्या होता है कि you have to okay. So there is only one TV in our house, so there is some kind of complicated negotiation about what channel will be watched. Okay. But I would like to go outdoors and just picnic, hiking.
Wonderful. Deepak, this has been extremely illuminating discussion we have had, and almost 2 hours is gone without actually me realizing the time which has passed. I am hoping that whatever has been discussed, a lot of the things can also be taken and also thought through further, because a lot of things have their own strands, and these strands are very beneficial for many of us to get more information. Any last words you would want to mention? You can just.
No, I think.
Yeah, but do you have any specific kind of plans right now in future? What do you want to kind of work on?
So I mean, I have many plans, but they don't work out.
Yes.
For example, we have been thinking of writing a textbook.
Oh, wonderful!
Somehow the project is more than 5 years old. It has not happened, but maybe it will. We try.
Yeah. all the best for that particular venture. And I'm again very thankful to you for spending this time and sharing all the thoughts.
Thank you very much.
Yeah, this is Pratidhvani, where we try to humanize science with one and only Professor Deepak.
Thank you, Pawan.